This is a lesson from section 2.4 in our statistics book. Section 2.4 is called Measures of Variation. We're specifically going to look at something that's towards the end of the section called the Empirical Rule. Now, the Empirical Rule is a rule that applies to data sets whose distributions are bell-shaped. And if you recall back when we were doing graphs, especially when we were doing like frequency polygons and histograms, and that what happens frequently with data sets is that the tops of those bars or the line itself in a frequency polygon tend to have this kind of bell-shaped distribution. It's very common in a lot of data sets, especially things that have to do with nature and people. For example, if any of you have children, when you take your baby to the doctor and they measure several things, and they'll talk about their weight and how they compare it to other babies of that gender and age and things like that. And the reason why they do that is they know a lot about that from collecting lots and lots and lots of data. It's known that these particular kinds of measures are a bell-shaped distribution, and when we know that that's true, it gives us lots of information about that data. As a quick review, remember that mu was population mean, like we were reviewing symbols for a little bit. Sigma was population standard deviation. Then X bar was sample mean, and S is the sample standard deviation. Now, if a data set is bell-shaped, then the mean, the data value that is the mean, will be right here in the middle, and it will be the highest frequency and it's going to be the most common. In a bell-shaped distribution, that mean is usually also the median, and it's also usually the most common. It's the mean, median, and mode. So this empirical rule that applies to bell-shaped distributions goes with a lot of different data sets, but we only apply these two distributions whose shape are bell. So if it was, I'm going to draw some weird ones, okay? So if it looked like that, or if it looked like this, or if it looked like this and went up and down, none of those would be bell-shaped distributions. So let's make note here that the empirical rule applies only to bell-shaped data distributions. And what happens in these bell-shaped distributions is that you have a very symmetric spreading, very symmetric distribution of the numbers. Sorry, I got stuck on my words. But spreading is a good word. Remember, variation, we talk about variation, it means spread. So when you have a bell-shaped distribution, you have the mean, median, and mode here in the middle. And then from there, it's very evenly spread. And then as you get further and further from the mean, then the frequency is lower and lower and lower. We don't say it ever actually gets to zero, but it gets smaller and smaller and smaller. Now let's look at how this is distributed. If you have a bell-shaped distribution, we've already said the mean is right here in the middle. And then notice how I've marked off, we're looking at a sample in this case. I called the mean X bar. And we're adding a standard deviation. So when we get to here, I've added 1 standard deviation. When I get to here, I've added 2, and here 3. And then going backwards, kind of think of it as a number line where the mean is the middle, of course. Then we subtract 1 standard deviation, then subtract 2 standard deviations, then subtract 3 standard deviations. And what the empirical rule says is that a certain percentage of the data values will fall within 1, 2, or 3 standard deviations of the mean. So let me show you what I mean here. So if you see, here's the mean right here in the middle. And if you go here, if you go between these two numbers, So that's plus 1 standard deviation and minus 1 standard deviation. So we would say those data values there in this pink area are within 1 standard deviation of the mean. Notice it's a pretty sizable chunk out of that bell. Okay? Now, the other name for the empirical rule is the 68, 95, 99.7 rule. And the reason why it's called that is because the percentage of data values that will fall here between 1 standard deviation below and 1 standard deviation above the mean will be 68%. 68% of the data values will fall between -1 and +1 of the mean, -1 standard deviation and +1 standard deviation of the mean. Now, if you go out 2 standard deviations, you get an even bigger piece of the bell. So let's look at that. So if we go 2 standard deviations, so 2 standard deviations to the right and 2 standard deviations to the left, and I'm going to draw an arrow all the way across. Notice that if you included all of that, just cut off those 2 tails there, that would be a really big chunk of that bell. And in fact, it is 95% of the data values will be within 2 standard deviations of the mean, meaning of all the data values there, if it's a bell-shaped distribution, 95% of them, that's a lot, will be somewhere between the mean minus 2 standard deviations and the mean plus 2 standard deviations. So if you wondered what the meaning of the standard deviation was before when we talked about how to find it, this was part of what we were using it for, is because this is known that standard deviation, part of how it's found is by determining how this spread is and where these natural cutoffs will be. So let's go on to 3 standard deviations from the mean. So 3 standard deviations from the mean. And you notice I have these equally spaced. That's because the standard deviation is the same. So I go over 1, 2, and I'm going to do an example for you in a minute where we actually use numbers, and then back 1 standard deviation, 2, and 3. So if I go from here all the way across to here, this orange arrow, that chunk of the bell represents data values that are within 3 standard deviations of the mean. And according to the empirical rule, when you have a bell-shaped distribution, 99.7% of the data values will be within that range of -3 standard deviations and +3. So this will be, and I didn't leave myself a lot of room, we'll put it over here, 99.7% are within 3 standard deviations. So 68% are within 1 standard deviation, 95% are within 2 standard deviations, and 99.7% of the data values are within 3 standard deviations of the mean if the data distribution is bell-shaped. Okay, so 68%, let's just put up here, are within 1 standard deviation. 95% are within 2 standard deviations, and 99.7% are within 3 standard deviations. Notice that 99.7%, that's really close to 100. In fact, if you round it to a whole number, it would be 100%. In fact, it is very rare for a data value to be more than 3 standard deviations from the mean. And in fact, remember that within 2 standard deviations is 95%. It's actually considered unusual to be outside of that. So think of that, 95%. That's pretty close to 100. And what's left for those 2 bits on either side there is 5%. So 2.5% over to the right, 2.5% over here. So anything that's outside of the 2 standard deviations is actually considered unusual, and definitely outside of 3 standard deviations is unusual and possibly even described as rare or extremely unusual or something like that. Okay, I have a problem here that I got out of the book. Let's look at this problem and see if we can figure it out. So we have a particular city, and the average utility bill in this particular city is $70. That sounds pretty good. Okay, so that is your X bar, your mean. If it was a population, it would be mu. Okay, so over here under X bar, I'm going to put that $70. There's my average utility bill for this city. Now, the other thing they've told me is the standard deviation. So that $8, that is the little s. If it was a population, we would call it little sigma. Okay, so if this is 8, if S is 8, then remember what we're going to do. We're going to try to figure out what these numbers are that mark off the 1, the +1, +2, +3 standard deviations, and then the -1, -2, -3 standard deviations. So as we move to the right, we're going to add 8 each time. So when we add 8 to this, this would be 78. Let's add another 8. This would be 86. Add another 8, and this would be 94. Now we're going to go backwards. Let's subtract 8 3 times. We're subtracting the standard deviation. So one standard deviation smaller than the mean would be $62. 70 minus 8. Then subtract 8 again. So 62 minus 8 would be $54. And then $54 minus 8 would be $46. Now let's talk about what this means. So we're assuming that the distribution of the utility bills for the city is bell-shaped, is a bell-shaped distribution. Otherwise, we can't use this problem. But if it is bell-shaped, then what we can say from this information is that 68% of the residents have a utility bill that's between $62 and $78. Remember, so within one standard deviation, remember, was 68%. Within 2 standard deviations, so that's from X bar minus 2 to X bar plus 2, that's going to be 95%. So that's going to be most of your residents then, 95% of them have a utility bill that's between $54 and $86. And then this last one, so almost everybody, 99.7%, have a utility bill between $46 and $94. So let's look at, and this is something you can do when you know a mean, when you've calculated a mean, and you've calculated the standard deviation like we talked about in our last lesson. Then if it's a bell-shaped distribution, you can figure out what percentage of the values you expect to fall within 1, 2, and 3 standard deviations. So let's look at the question. Here's the question here. I don't know if you can see it, but it says, between what 2 values do about 95% of the data lie? Well, we already identified that. That's going from -2 to +2 standard deviations. So the answer to that would be from 54 to $86. And that would be the answer to that question. There are other types of questions that you can answer using the empirical rule. This is just one example. We'll go through other examples when we have class. Okay. Now, you may be asking, well, what if the distribution isn't bell-shaped? Then how do you know what percent will be within 1 or 2 or 3 standard deviations? Well, for that you have to use a different rule. So in another lesson, we're going to talk about what to do if it's not a bell-shaped distribution. And that will be a little bit different, but it's not hard. It's just a little bit different. Okay, so this is your 68, 95, 99.7 rule. So use this picture and use this information to help you with any of the problems in the homework from 2.4 that have to do with empirical rule.